Hi, today we'll do our discussion on Stokes' theorem. We'll start with this first example. Evaluate the integral of f over c, where f is the vector field with components c squared, y squared, and x, and c is the boundary of the portion of the plane x plus y plus z equal to 1 in the first octant. To see the benefit of your Stokes' theorem, we take a look at the sketch of your plane here. Notice that what we have here for C is essentially this triangle connecting the points 1, 0, 0, 0, 1, 0, and 0, 0, 1. So to evaluate by definition entails that we have to evaluate the integral over this line, and this line, which will in turn imply that we need three different parameterizations for those lines. Tedious process at that. So instead, we'll proceed using Stokes' theorem by first finding the normal vector. So given this plane, you'll have your normal vector to be actually just 1, 1, 1. Okay. We now find the curl of your vector field f. Your curl is again given by this determinant. So we start with your first component. The first component will be partial of x with respect to y, which is 0, partial of um, y squared with respect to z, which is also 0. So you get 0 minus 0 for your first component. For your second component, you get partial of z squared with respect to z, which is 2z, and partial of x with respect to x, which is 1. So you get 2z minus 1. And finally, for the last component, you get y squared with respect to x, which is 0, and z squared with respect to y, which is also 0. Simplifying, you get 0 equal to 2z minus 1. By Stokes' theorem, we now have our ingredients ready. You have your curl, and you have your normal vector, essentially. So by Stokes' theorem, your line integral is just equal to the surface integral of the curl of your vector field f. Okay? Over the surface S, which is given essentially by the plane x plus y plus z equal to 1 in the first octant. Okay? So we evaluate this now by replacing curl f here by this vector and the normal vector by 1, 1, 1. So you get this 0, 2z minus 1, 0, dot with 1, 1, 1. D here is the projection of your solid onto the xy plane. So what we have here for your dot is 2z minus 1, and the projection of your solid onto the xy plane is just triangle, bounded by the x, the y, and the x and the y axis, and the line y equal to 1 minus x. So in terms of double integrals, that projection is given by 0 to 1 for x and 0 to 1 minus x for y. So we get 2z minus 1, but we want integral with variables x and y only, so we replace z by 1 minus x minus y. So you'll get 2 minus 2x minus 2y minus 1, which simplifies to 1 minus 2x minus 2y. The first two terms of this integrand does not have a y, so to integrate that is just multiplication by y. And then for the last term rather, you'll just have y squared over 2. The 2 will cancel out. This is for evaluation from 0 to 1 minus x. So you'll get 1 minus 2x times 1 minus x, and subtract from that the square of 1 minus x. This simplifies x squared minus x. Kindly verify. For evaluation or for integration from 0 to 1. The antiderivative is, of course, x cubed minus x cubed over 3 minus x squared over 2. Evaluate again from 0 to 1. The evaluation at 1 is 1/3. The evaluation, the second term at 1 is 1/2. So you get 1/3 minus 1/2 minus 0. You get negative 1/6 for your final answer. Okay. For this example, your vector field f is given by the components 2yz, xc, and xy. Your c is the boundary of the surface parameterized by r of uv, given by the components u cosine b, u sine b, and u squared sine squared b, where u is in 0, 1, and b is in 0 to 2 pi. So we begin by finding the curl of your vector field f, again given by this determinant. So we start by taking a look at the first component, it's just given by the difference of the partial of this with respect to y, which is x, the partial of this with respect to z, which is also x. So you have your first component to be 0 actually. For your second component, we take the partial of this with respect to z, you'll get 2y, minus the partial of this with respect to x, which is y. So you'll get 2y minus y. And then finally, for the last component, you take the partial of this with respect to x, which is c, minus the partial of this with respect to y, which is negative 2c. Simplifying, you get your curl to be given by the vector 0, y negative z. As for your normal vector, we have to first uh, differentiate your parameterization r, with respect to u and with respect to v. So for instance, with respect to u, we get this derivative is just cosine b, or partial derivative with respect to u, you get cosine b. This with respect to u will become sine b, and this with respect to u will of course become 2u sine squared b. With respect to b on the other end, cosine b will become negative sine b will become cosine b, and sine squared b will become 2 sine b cosine b. So you'll have 2u squared sine b cosine b for the last component of r sub v. We take the cross of these two vectors, r sub u and r sub v. We get for your first component of the cross a product of this and this, which is 2u squared sine squared b cosine b. Now, if you take a look at the product of this component with this component, you'll actually get the same thing. So taking their difference, the first component of the cross is just 0. For the second component of the cross, we take the product of 2u rather sine squared b and negative u sine b. So you'll get negative 2u squared sine cube b. And subtract from there the difference of this component with this component, which is actually negative 2u squared sine b cosine squared b. There is a common factor. The common factor is negative 2u squared sine of b. If you factor that out, the other factor will actually be cosine squared b plus sine squared b, which is just equal to 1. So uh, this gives us, for your second component of the cross, negative 2u squared sine v. And for the last component of your cross, you just take the product of this component with this one. That's u cosine squared b. And then subtract from there the product of this two components, which is negative u sine squared b. So you take the difference, you'll get u multiplied by cosine squared b plus sine squared b, which is again 1. So you'll just get u for your last component. So this is again our curl. Our curl is 0, y, negative z. Our normal vector is 0, negative 2u squared sine b, comma u. So by Stokes' theorem, this integral can be written as a surface integral, which is then equal to this double integral. Um, Here you have your curl, and here you have your normal vector. We replace y and z in terms of u and v. By taking a look at the parameterization r, you just get u sine v again for y, and for z, you get u squared sine squared b. Here, we have already replaced your double integral, or rather, we have already inserted our limits of integration for your double integral. It's as simple as the bounds of your intervals for u and v. So for u, you have the integral must run from 0 to 1, and for your v, you have your integral running from 0 to 2 pi. So our integral is a dot product of these two vectors. So if you take the dot, you'll actually get for your first component, is, I mean, the dot of the first component is just 0. The product of the second components is negative 2 u cubed sine squared b. And for the product of the third components, you'll have negative u cubed sine squared b. So you'll actually just, common terms, you combine them, you just get negative 3 u cubed sine squared b. We now integrate this double integral by writing it out as a product of two integrals with respect to u and with respect to v. So you'll get negative 3. Let's bring out negative 3 from the integrals. You'll get negative 3, a constant of that, so multiplied by the integral of u cubed from 0 to 1, multiplied by the integral of sine squared of b from 0 to 2 pi. But from Math 22, in order to integrate those integral, you have to write it as 1 minus cosine 2b over 2. So now we're ready to integrate these two integrals. The integral of u cubed with respect to u is of course u to the 4 over 4. The integral of 1/2 with respect to v is 1/2 v. For the integration of cosine 2v, it will become sine 2v over 2. Combine it to the 2, you'll get a sine 2b over 4. So you'll get here, integration of 1/2 is b halves. Integration of cosine of 2v over 2 is sine of 2v over 4. We evaluate this at 0 and at 1, or from 0 to 1. So evaluation at 1 is just 1/4. So you'll get negative 3 times 1/4 minus the evaluation at 0, which is of course 0. For the second factor, or for this factor rather, if you evaluate this v halves at 2 pi, you'll just get pi. If you evaluate this at 2 pi, you'll get 0. If you evaluate this at 0, you'll get 0. And if you evaluate this at 0, you'll get 0. So this whole thing is actually just pi. So you'll get negative 3 times 1/4 times pi. Therefore, your final answer is just negative 3 pi over 4. For this example, you have your vector field f given by the components x, comma z, comma 2y, and c is the intersection of the planes, or the plane rather, x equal to z, and the cylinder x squared plus y squared equal to 1. So here we have a nice sketch of the intersection and the surface that is covered. So we have a nice sketch, a little bit problem, the coloring here perhaps. So again, you have your cylinder, x squared plus y squared equal to 1, and you have your plane x equal to c, giving us this very nice intersection. So instead of computing the integral over the intersection, we just take a look at, or we just use your Stokes theorem by first finding the curl of your vector field f. Again, your curl is given by this, which is equal to first component partial of 2y with respect to y minus partial of z with respect to z. That's 2 minus 1. Next component is partial of x with respect to z minus partial of y with respect to x, which is 0 minus 0. And for the last component, you have partial of z with respect to x minus partial of x with respect to y, which is, again, 0 minus 0. So the curl of your vector field f is actually just 1 comma 0 comma 0. So here we also want your normal vector for your uh, surface. In this case, your plane, x equal to c essentially, bounded by the curve of intersection. So your normal vector will just be given by negative 1, 0, 1. So here, for this example, our curl is again 1, 0, 0, and our normal vector is negative 1, 0, 1. This curl and this normal vector will actually simplify our computation a little bit because of this. By Stokes' theorem, we can therefore write it as, again, dot of the curl of your vector field f and your normal vector, which is just given by 1, 0, 0 and negative 1, 0, 1. So if you take the dot, that is just negative 1. Now, D here is the projection of your surface bounded by the curve of intersection onto the xy plane. But as we all know, that surface is bounded by x squared plus y squared equal to 1, the cylinder. So the projection is essentially the circle centered at the origin of radius 1 on the xy plane. So you'll just have uh, that x squared plus y squared equal to 1 when z equal to 0 as your projection or as your d here. Note here that we have a constant integrand, and for double integrals, when this is the case, you just multiply that constant um, with the area to get the evaluation. And the area of that projection of that circle of radius 1 is, of course, 2 pi. And here we'll have, for the next line, negative 1 to be multiplied by the area, of course, which is 2 pi, area of the database. So our final answer should be negative 2 pi. For this example, your vector field f is given with the component sine x minus y cubed over 3, comma, cosine y plus x cubed over 3, comma, xyz, and your c is the boundary of the cone z equal to square root of x squared plus y squared that is below the plane z equal to 1. Essentially, your c is a circle on the z equal to 1 plane of radius 1. uh, Question here is why don't we just use the definition of your line integral using the parameterization for the circle? Well, a parameterization for the circle goes like this: r of t equal to cosine t sine t comma 1. And in order for us to evaluate the line integral using the usual definition, we have to plug in those cosine t sine t here and here, which will yield sine of cosine of cosine t, and I don't think it's very recommended to perform integration with those expressions, sine of sine t, cosine of cosine t, and so on. So instead, we'll proceed using Stokes' theorem. So for Stokes' theorem, we consider the surface instead, bounded by your um, curve C. And that surface is essentially the plane is equal to 1, that circular surface there. Now, we need, of course, your normal vector. The normal vector for the plane is as simple as 0, 0, 1, of course. The normal vector is parallel to your positive z-axis. We also need your curl of your vector field f. So we compute the curl as given by this. The first component will be the partial derivative of xyz with respect to y, which is xe, minus the partial derivative of this with respect to c, which is 0. So you get xe for the first component. For the second component, you have partial of this with respect to z, which is 0, and then minus partial of this with respect to x, which is yc. So you'll get negative yc for your second component. For the third component, you have partial of this with respect to x, So that's 3x squared over 3, which is just x squared, minus partial of this with respect to y, which is, excuse me, negative 3y squared over 3, which is negative y squared. So you'll get negative will become positive. You'll have x squared plus y squared. So by Stokes' theorem, your line integral is now a surface integral, or can be written as a surface integral, with your integrand given by the curl. This is the curl again, dot with your normal vector, which is again, as we recall, the normal vector for this example is 0, 0, 1. The projection onto the xy plane is actually, since you have a circular surface on the z equal to 1 plane of radius 1, centered at the z equal at the 0, 0, 1 point. If you project that onto the xy plane, you just get the same circle essentially, which is a circle centered at the origin of radius 1. Now, if you take the dot here, let's take a look at the dot. The dot is just x squared plus y squared. Here, this whole double integral screams or begs that it be solved using polar coordinates. There's an x squared plus y squared, which in polar coordinates is of course just r squared. More so, your bound, your d here is just a circular region, which we can easily find your theta bounds and your r bounds. In fact, since it's a complete circle of radius 1, your theta bounds will be from 0 to 2 pi, whereas your r bounds will be from 0 to 1. We have this as your integral. You'll have your theta bounds again 0 to 2 pi, r bounds 0 to 1. We replace x squared plus y squared by r squared, and do not forget, instead of just inputting dr, d theta, we must include r here. So you get r dr d theta, and you get r cubed essentially for your integrand. There's no theta in your integral, so integration with respect to theta will actually yield just the length of the interval from 0 to 2 pi, which is 2 pi. So you'll get 2 pi multiplied by essentially the integral of r cubed with respect to r evaluate from 0 to 1. That's r to the 4 over 4 for evaluation from 0 to 1. So the evaluation at 1 is of course 1/4. The evaluation at 0 is 0. So if you take the product of 2 pi and 1/4, you get your final answer, which is of course pi over 2. This time you're given a surface integral involving the curl of your vector field f, where your f is given by the component c comma x comma y, and your surface s is the paraboloid z equal to x squared plus y squared that is below the plane z equal to 1. So if you take a look at the sketch, you'll have this one. Notice that here we have a curve c, right? The intersection of planes equal to 1, and your surface S is actually the curve C on the equal to 1 plane, the circle of radius 1, which is of course given by this parametrization. C uh, is given with the parametrization r of t equal to cosine t sine t comma 1, where t runs from 0 to 2 pi. So we have your vector field, and you have your what do you call this, your parametrization for your curve C. So instead of computing the curl, computing or finding the normal vector and taking the dot, a long process of that, since we have a nice parametrization of your boundary curve, we can just use Stokes theorem. So this curl f is just a line integral, where we have your integral running of course from 0 to 2 pi. We replace every x, y, z in f by the corresponding parametric expressions in terms of t. So for instance, you'll have z to be 1, x in the second component will become cosine t, and the last component will become sine t. And of course, this will be dotted with your derivative of your parametrization r, which in this case happens to be negative sine t cosine t comma 0. So if you take the dot, you'll just get negative sine t plus the square of cosine of t. Integral still running from 0 to 2 pi. The antiderivative are perhaps the best first to write cosine squared t. Using Math 22 technique, this is just 1 plus cosine of 2t over 2. So integrate now with respect to t. The antiderivative of negative sine t is of course positive cosine t. The antiderivative of 1/2 with respect to t is 1/2 t. The antiderivative of cosine 2t over 2 is sine 2t over 4. So you get this antiderivative again, cosine t plus 1/2 t plus 1/4 sine of 2t for evaluation from 0 to 2 pi. There's a lot of uh, evaluations here that will be 0. For instance, evaluation of course at 0 for these two terms will be 0. Evaluation of sine 2t at 2 pi will also be 0. Evaluation of cosine t at 2 pi and 0 will both be 1. So that's 1 minus 1. Those will cancel out. So essentially, out of all the 6 evaluations that you will do for this antiderivative, the only one that will be left will be the evaluation of this term at 2 pi. And that is 1 half t evaluated at 2 pi, you'll get pi. So 2 pi over 2 is just pi. So you get your final answer here, which is pi. Here we have your vector field f given by 3y, 4z, and negative 6x as components. And your s is the paraboloid c equal to 16 minus x squared minus y squared above the xy plane. So here's a rough sketch. Not so pretty, pero pwede na. You'll have your surface integral involving the curl. So instead of doing that, we'll use Stokes' theorem to just work with the boundary curve, which essentially is this circle here on the xy plane. This is, of course, when z equal to 0, you'll just get x squared plus y squared equal to 16, which is a circle of radius 4. As such, the boundary curve c can be parameterized as r of t equal to 4 cosine t, 4 sine t, comma 0, 0 because on the c equal to 0 plane or the xy plane, uh, is where we can see or we can find your boundary curve. Here t runs from 0 to 2 pi. So we can just write by Stokes' theorem again. This is just the integral from 0 to 2 pi. We replace every x by 4 cosine t, every y by 4 sine t, and every c by 0 to get this. You'll get 12 sine t, 0, negative 24 cosine t to be dotted with your derivative of r, which is, of course, negative 4 sine t, 4 cosine t. So the second and the third component happily is just 0. So you'll have only for the dot negative 48 sine squared t. So write it out as in terms of your Math 22 identity, you'll have 1 minus cosine 2t over 2. So that negative 48 will become just a negative 24. Integrate, you'll get t minus sine of 2t over 2, evaluation at 0 to 2 pi. The evaluation of this at both 0 and 2 pi is 0. The evaluation of t at 0, of course, is of course 0. And you're left with the evaluation at t of t rather at 2 pi, which is of course 2 pi. So you'll get for your final answer negative 24 times 2 pi, which is of course negative 48 pi. Here you have your surface integral of the curl of the vector field f given by the components x, comma y, and s is the hemisphere x squared plus y squared plus c squared equal to 1 above the xy plane. So here's a not so nice sketch, but yeah, we'll just work with this one. You just use your power of imagination to see that this is actually the hemisphere S. Okay. So we'll have a look at the boundary curve here, C, let's say, which is essentially a circle of radius 1 on the xy plane centered at the origin. So we can easily parameterize that. We get cosine t sine t 0, where t here runs from 0 to 2 pi. We can apply your Stokes' theorem with this vector field and this parameterization and write out this line integral as integral from 0 to 2 pi. These are the bounds for your t, your parameter t. And for the dot product, we'll take the dot product of f of rt. So to get f of rt, we'll replace every x here by cosine t and every y by sine t. Okay? So you'll get cosine t, comma sine t, dot with the derivative of r of t, which is negative sine t cosine t, comma 0. If you take the dot, you'll just get negative sine t cosine t plus cosine squared t. Let's write out cosine squared t as 1 plus cosine 2t over 2. Integrate with respect to t, you'll get, for the first term, a negative sine squared t over 2. For the second term, you write it out separately as 1 half integrated, that will become 1 half t, and cosine 2t over 2 integrated becomes sine 2t over 4. And this is, of course, for evaluation from 0 to 2 pi. The signs here, no, the sine of t and the sine of 2t evaluated at 0 and 2 pi will both be 0. Rather, will all be 0, the evaluations that is. 1 half of t evaluated 0 is 0, evaluated 2 pi is, of course, pi. So you'll get, for your final answer for this example, it's just pi.